All right, let's talk about network data. So, with network data, this is in contrast to things like tabular data, where you just have items. Now, what we're trying to do is think about where we don't just have items, we're going to call them nodes in this case, but we also have links. So, these are relationships between things. Sometimes they're called networks, sometimes they're called graphs. Um, Now, let's talk about trees. Those are a special case of networks where we don't have cycles. That's the technical term. That is, there's only one parent for each node. So, what's interesting about networks is that now we can think about tasks that depend not only on, about the attributes, which we've been talking about quite a lot, but also just based on topology, that is the structure of these relationships between the nodes. So we can do things like find paths, we can find topological neighbors, we can even do more complex things like say, well, considering the topological structure of this graph, which things are more central rather than less central if we think about only being able to move from between nodes from hop to hop. Those are usually called centrality measures or sometimes importance measures. We might want to find things like, well, where are there really tight interconnections? Those are often called clusters or communities. And that's the kind of task that is fundamentally about topological structure. It's not a task you could do if you were thinking about just tabular data. But what we can do, just like with tabular data, is we can have attributes on the nodes or on the links or both. And so there can be a lot of attribute-driven tasks. And of course, it's the combinations that have both that particularly get interesting in this case. Like, imagine saying that I have a network where nodes are people and a link is between them if they are friends with each other. And there's attributes like what's their favorite animals, and that would be an attribute on the nodes. So imagine that I was saying, okay, so if I want to find the friends of friends who like cats, I'd have to take the node, do a one hop traversal to find the adjacent nodes to that given node, and then check the attributes of every one of those nodes and say, hey, does this person like cats? Now, if they're good people, they would say yes, but we'll see. So, for node link diagrams, that is a very, very common family of idioms for showing networks. It's probably so obvious to you, you maybe didn't even think about it as a choice. If someone asked you to draw a sketch on a napkin, you'd probably draw it this way. You would draw points for the nodes, and in our multi-level approach, let's think of that as a level one thing. So we have this low level of the points, which are the marks that represent the nodes, and then we're going to connect them up. And well, we're going to do that the obvious way. We're going to draw a link between them. We're going to draw a segment. Because this is you could think about it as a path in general, but with these kind of simple graphs, we just have one node connected to the other. So that's a two pair thing. So we've got this pairwise segment. Now, as we've seen before, a segment could be just an actual straight line. It could be an arc. Those are both legitimate. Um, and in our analysis, where we think about levels, we're going to actually do a multi-level analysis here because typically with almost all graph drawing algorithms, the node locations are what control the place where the links go. Um, so basically, the link positions are inherited from those node locations. And so typically with node link diagrams, we can make choices about position and order for the nodes, but we don't make those choices for the links because those are just routed in between them. The other thing that's really important about this kind of segment is this is a connecting segment. Its job is to connect things. It's not like the kinds of segments we see in, say, a bar chart where they're actually size coding an independent attribute. So these segments are showing connections between nodes. They are not expressing the length of a quantitative attribute. And that means that length is unavailable. We can't additionally size code these links because then they wouldn't actually show that connection. Um, so like I said, this is quite intuitive. It's familiar. There's a lot of variants of this. So when I say node link diagrams, that doesn't kind of fully nail something down. I can't actually tell you everything there's to say about how the channels are used because there's so very many possibilities here. It could be networks, it could be trees, it could be used in conjunction with things like geographic maps. You might have so there's all kinds of things we could do here. Now, how do you do a good one of these? Well, it turns out people have thought about this for many, many decades. And one way to think through this is, well, what are we trying to maximize? What are we trying to minimize? So you could say things like, well, we try to avoid having the edge cross because they sort of your attention is drawn. If you've got an edge crossing, you look at that spot they cross, but it doesn't really mean anything. So we try to avoid things like overlaps between the nodes. If things are neighbors topologically, then it's nice if they're neighbors geometrically. If the layout actually shows topological neighbors as geometrically close to each other. Now this gets complicated, as we'll see. You often want to minimize the total drawing area. If you do allow bends of edges, you want to try to minimize those. There's things we want to maximize too. You might want to maximize the angular distance between different edges. Because if they're too close to each other, it can get kind of hard to follow the path through the graph. It's hard to tell, oh, is that line on top of the other line or not? So maximizing that angular distance can actually make it easier to read. Um, we typically want to avoid big disparities in aspect ratios. So close to a square is usually what people are aiming for. If you're really tall and very um, not very fat, then it's hard to see. Or likewise, if you're very, very wide, but then that's more difficult to see. So typically we're trying to minimize those. Um, Now it's particularly tricky, but when possible, you want to emphasize symmetries. So if there are identical substructures in graphs, then you'd like those to look similar in the layout of the graph. Well, what's hard about this? Turns out everything is hard about this. Any individual criterion is typically NP hard, which is, of course, a way of measuring the algorithmic complexity of that. Um, Worse yet, a lot of them are in direct conflict with each other. So here we see some examples of if you're trying to minimize the number of edge crossings, then sometimes that means you use more space than you might have to. If you want to keep edge lengths as uniform as possible, then that can violate the attempt to try to show symmetry. So the tricky thing is this is a very hard computational problem. Um, and it's not something that we're going to be able to just say, oh, let's trivially solve this. What that means is we end up using a lot of heuristics. We end up using a lot of custom algorithms trying to take one or another particular thing and optimize for that because there's not really a good way to just globally solve this problem for one time and for all. So with optimization-based layouts, what people do is they try to formulate this layout question just as a straight-up optimization problem, and then all these criteria can be some sort of a cost function. So you can say, well, I want to have a weight on how much it matters if there's crossings, how much it matters if it's sprawling versus compact. And then there's a lot of algorithms out there for doing optimization where you can try to find a layout that satisfies all those constraints. Um, there's a whole suite of basically heavily related techniques that we're going to all think about together. Sometimes they're called energy-based physics models or force-directed placement or spring embedders. For our purposes, we can just think of these as all being essentially the same. So what is going on? With force-directed placement, you can think of it as a physics model where a link is a spring trying to pull things together, but the node is a magnet trying to have a repelling force that uh, pushes them apart. Um, and so the way force directed placement works is you just start out by placing everything randomly, and then you have this iterative loop where you calculate the forces with the repulsion forces and the attraction forces, and it iterates towards some sort of solution. If you're lucky, it converges reasonably quickly. Um, Now, what's interesting about this is, well, the strengths are that we can actually, if the graph is pretty small and pretty sparse, not too dense, not too many links compared to the number of nodes, it's going to do something reasonable. Typically, you can see some cluster structure. Typically, the edge lengths are going to be roughly uniform. What's tricky about this, though, is it's not deterministic. That part where we lay things out randomly at the beginning is going to have implications. Um, it's also quite expensive computationally. It's an n-cubed algorithm if you've got n nodes. Each one of those steps where you're updating the forces is n squared, and usually takes about n cycles to hit some sort of convergence point. So the naive force-directed placement doesn't scale too well past about 1,000 nodes. There's certainly ways of being more sophisticated, but the basic one is not going to scale too much. From a purely computational point of view, also there's perceptual issues in the amount of edge clutter that you often get. Now, you can actually show that process of iteration. Be aware that although it's sort of engaging, it can be somewhat distracting. So, if you're going to use this yourself, think carefully about whether you actually want to make that iterative process visible to the user or not. So, let's analyze this. Force-directed placement, from a visual encoding point of view, well, we've got these link marks, and the mark type is a segment, and these are specifically connection marks. And then we have these point marks, which are the nodes. So at level 1, we've got the nodes, and then those positions are used at a level above with the links to inherit those positions. Don't have any shared boundaries. So what is going on with our channels? Well, the thing is, position and order and also orientation, they're not available. So there's no meaning directly encoded, but the algorithm is using this to do things like try to minimize the number of edge crossings. So we have this interesting situation where it doesn't mean anything, but it's not available for anything else. And the hard question is, well, does it mean something if two things are next to each other? Is proximity something that has semantic meaning? And the answer is sometimes. Sometimes it does mean something. Sometimes it's just a completely arbitrary outcome of the algorithm. And so being able to sort out which is a tricky situation. So there's also another interesting tension in terms of length, which is long edges really jump out at you, but actually, in many cases, you're trying to have the edges be as short as possible to show that things are topologically next to each other. So there's also a bit of perceptual tension there. So what's free? Well, we can certainly color code. We can shape code using symbols for the nodes. We could also use things like line styles for the links, like dotted lines or wavy lines or other things like that. You can size code the links in the other direction. So you could width code the links, even though you can't length code them. And you could use 1 or 2D size coding for the nodes. So these are all possible. The kind of task people are doing here is they're exploring topological structure typically. So they're trying to locate paths of going from one node to the other and trace along how you do that. They're often trying to find clusters. You can see in this diagram here, like the purple nodes are forming a cluster and the orange nodes are mostly clustered, but not quite as tightly. So in this case, we see sometimes the color coding is following that cluster structure and sometimes it's not. Now for scale, we typically would want to be doing this kind of node link diagram when by graph theoretic standards, they're relatively sparse. So if you have more than 3 or 4 times the number of nodes for the edge count, things are going to get very, very, very dense. There's people talk about hairballs a lot in graph drawing, and it's just you can't actually see what's going on. There's too much overplotting from occlusion. What are some other things we could do? Well, we could do circular layouts or arc diagrams. And think of this as a special case of node link diagrams where there's restrictions. So you could lay out the nodes around a circle or along a line. So we have that original data, the network, but we also are going to derive an attribute that we're going to use for ordering the nodes. Now, typically, that's, again, this idea of we have an algorithm that's working on this. So to do something like minimize the edge crossings, that would be algorithmically determined and then stored as some derived attribute. So the channels for this are just like before, position and order are used algorithmically. They don't show you something direct that's in the data, but they've done something where they've analyzed the topological structure of it and tried to do things like minimize crossings. As before, things like color and shape and orientation are free to be used, at least the orientation for the nodes, if you had an explicit representation of the nodes as a shape. An example at the bottom here is showing how that node ordering is pretty crucial to just avoid something that's difficult to read because of too much clutter. On the left, you've got that before you did any specialized ordering, just essentially in some random order, and you see a lot of clutter in the middle. Whereas on the right, with a particular approach called barycentric ordering, you're seeing a lot more structure, right? You're much more able to actually interpret what's going on in that graph. Same thing for the linear, when you've got the nodes arranged along the line and then you're drawing them as arcs, these arc diagrams. The one on the left, lots of clutter. The one on the right has substantially more visible structure. It's the same data, the same network, but we've had a algorithmic ordering applied to those nodes. Okay, well, what else could we do? Um, we could basically derive an adjacency matrix from the network. So, and these are called, unsurprisingly, adjacency matrix representations. So, what's going on there? Um, so we can say, all right, let's think about the nodes that are connected by an edge, and we're going to just construct a matrix where we say, well, here's all the nodes, um, and then here's all the nodes in the other direction as well. And with that table of data, we're going to try to say, okay, let's actually represent the edges. So you can see in this one where we've got a hub with some spokes, we just see that that corresponds to a line in that adjacency matrix. In the upper right, we see, oh, these are fully connected. It's called a clique. And we see this visible structure in the matrix. Or we see this sort of structure here where A and B are not connected to each other, but both of them are fully connected to C and D and E. Again, we see a sort of contiguous block in the matrix here. And then we can start to see, more and more structures where we see, oh, we've lit up a cell here at the intersection of both of those node lines for the rows and the columns, and that shows us we've got a link. Now, it matters a lot, just like we saw with the arc diagrams and the circle diagrams, the order of the nodes matters immensely for being able to pull out patterns. Here's two examples of relationships between characters in Les Miserables. This is one of the D3 blocks that Mike Bostock made. And on the left, we've just ordered all the people alphabetically by their names. We're not seeing a lot of structure. On the right, they've run an algorithm to actually explicitly try to capture the structure that's in that network. And we see much more interesting stuff along the diagonal. So we are able to actually see, oh, clearly there's some groups of characters that do a lot of interaction together in that novel. Um, so that's an example of how the order matters quite a bit. So adjacency matrix views can be good for certain kinds of topology tasks. Um, so anything related to things like a one-hop neighborhood, everything directly reachable in a single hop, they're actually quite good for that. Notice how you can just look up for node B and go along on a row and be guaranteed that you easily see everything that's connected to B. Um, on the other hand, path tracing is actually quite hard. It's if we look at the node link graph on the right side, well, we can definitely see A to E to C to B. That's pretty easy to read off. It's much, much harder to read that off from the adjacency matrix view. You'd have to do quite a lot of cognitive effort to do that. It's not absolutely impossible, but it's definitely hard. It's not well supported by your perceptual system. Some structures are visible in both. Things like cliques, where things are fully connected to each other. If you use appropriate reordering, then you can see those in these adjacency matrix views. Or bicliques, or clusters, which is that they're, kind of near cliques but not completely. So these structures can be made visible in adjacency matrix views with the correct ordering algorithm. Okay, so let's analyze this. What have we got? Well, we take our data, which is network data, and we transform that basically using the same kind of visual encoding as we would if it were a heat map. So what we do is we derive a table. We have our original network data, and then we say, oh, is there an edge between the nodes? And then we take these nodes and make a list of them, and we actually build a table from the network. Now, typically, in order to be useful, we also have this quantitative attribute that we derive, which is a node ordering. Usually that's done by considering the entire two-dimensional structure of the matrix, not just one side or the other side at once. Um, and the idea is we want to somehow have a way to maximize the visible patterns. So from a visual encoding point of view, what are we doing? Well, this is just like a heat map. So we have point marks that have shared boundaries in this grid structure. If the cell is on, that's showing the presence or absence of an edge. And you can see here we've got some adjacency matrix views side by side with a node link view of the same graph for a really, really small one and a slightly more substantial one. What about the channels? Well, remember, this is another case of where the algorithm is actually being used to try to minimize, in this case, not edge crossings, but to maximize the structure of these sort of cluster style visual patterns. So they're not available to encode anything else, right? They're used by the algorithm for the layout itself. Because it's one of these shared boundary situations, then we can't change things like the size or the orientation or the shape of those. But we certainly can color code, and it's very commonly used to actually show things like you could have a weighted count if you have a weighted graph, not just an unweighted graph. Um, and then our scalability, much like with the heat maps, or is in the very limit. If we had 1,000 nodes by 1,000 nodes on a 1,000 by 1,000 pixel screen, then in the limit we could handle up to 1 million edges, but certainly no more. So let's compare these two approaches. Well, node link diagrams are really good for understanding a lot of aspects of topological structure, particularly anything involving tracing a path. They're intuitive, they're very flexible, people typically don't need training. The adjacency matrix is an approach that is focused much more on the edges than on the nodes. Um, what's nice about them is it is straightforward to lay them out. You do have to do a reordering computation, but then after that, the visual encoding itself isn't very complex. It's just like a heat map. It's also nice that you can predict the amount of screen real estate you need. That's not easy to predict with a node link layout, but it's absolutely fixed in stone once you know the number of nodes in the graph with an adjacency matrix view. And thus, you also have really nice scalability. And in particular, you don't have that clutter of all of the edges on top of each other, that so-called hairball problem that you have with node link views. Some topology tasks are trainable, so you can certainly teach people how to do those. So people have done some empirical studies on this. There was a very fundamental paper that just got the 20-year Test of Time Award last year from Goniam et al. That showed that if you've got a small network, node links are great. But if you've got a large network, then if you don't have to do anything involving path tracing, then the matrix can be quite good. On the other hand, if you have to do path tracing, it's tricky, and this is why people spend a lot of effort on coming up with graph drawing algorithms, because then neither one of those algorithms is great, and you need to do something more specialized. So people have invented all kinds of different hybrid solutions. Here's one called node tricks, where people try to say, oh, what if we tried to have the best of both worlds? Where things are dense, we'll have a little teeny adjacency matrix. Where things are less dense, maybe we'll try the node link graphs. So these kinds of things have been pursued. Let's take a minute to talk about the special case of trees. So we can use the same big idea. We can certainly have node link drawings of trees. And there's a lot of algorithms for exploiting the fact that you've got this really strong knowledge of hierarchical structure in a tree compared to a general graph. So there's a family of algorithms that I'll come back to an approach back in the 80s from Reingold and Tilford for doing smart drawings of trees where you are exploiting that parent-child structure and you're trying to explicitly capture it in the visual encoding. So you're trying to be as compact as possible, but avoid overlaps. And there's both rectilinear variants, like we see on the left, with Cartesian coordinates, and radial approaches with polar coordinates that are basically the same basic idea, but variants of that. For those who do want to end up getting into this for project work, there's a nice algorithm write-up about what's going on with that on this page. These are also direct links to D3 blocks implementing these. So let's analyze this. With a radial node link tree, our data is a tree, which is that special case of network. And so we're doing the same thing. It's a node link approach. We've got the node marks on level 1 that are points. And then we've got for the links, we're showing segments, which are connection marks. You can see here we've actually got arcs rather than just straight lines. And that's at level 2, and they're inheriting the position from the nodes. So what are we encoding? Well, with this radial tree, the radial position, and thus also the order, is showing you the depth in the tree. So the root's at the center, and you can just look up what is the depth in the tree at any particular radial location. Now, what about the angular position? Well, for the nodes, there is an ordering where siblings of the same parent are all next to each other, and they're laid out in order. And so that's typically done by having some attribute. It might be a not very smart one, like in this case, we're just using alphabetical order of the labels, or it might be something more complex. Now, notice how what's unavailable is angular position. The order is being used, but the position's actually arbitrary. We could spin this entire tree around and it would not change the meaning of anything. So it's really, there's something asymmetric here where depth out from the center is something that's meaningful, but the actual position of the angular position is not. Now, just like with other node link graphs, the length of the segment, that we can't use that to encode anything else. It just depends on the node position. And so also the orientation of the segment is also unavailable. Now, nodes can be sized in 1D or in 2D, and the width of links, so the line width, can also be something that's under attribute control. So we can have any shape we want for the nodes. If that's an asymmetric shape, then we could even have the orientation down at the node level. So what are these good for? They're great for understanding topological structure, for following paths. So these sort of inherit the strengths of node link diagrams in general. For the scalability, if you needed to actually read the labels, then, maybe around 1,000 nodes would be the limit on a 1,000 by 1,000 pixel screen. If you were just needing to show the topological structure of the tree and didn't need to read the labels, maybe you could get up to, say, 10,000 or so. So what else could we do with trees? Well, we can do something interesting here. So let's say we have a tree, and not just that, but we also, at each of the leaf nodes of the tree, the bottommost nodes, the ones with no children, what if we had a quantitative attribute? Well, then we could use a containment mark to actually show that hierarchical structure. So instead of drawing a line, we're going to enclose. So if we show that hierarchical structure with polys, then we can, in this case, what we're going to do is we're going to have a carefully everything fit together approach. So we're going to have shared boundaries, two-dimensional shared boundaries, showing the hierarchical structure of this tree. And that's what we're seeing here on the right. So let's break that down. We've got an explicit encoding. We are encoding the two-dimensional size, or rather, we're encoding the attribute with the 2D size, which is area. We're again in a situation where horizontal and vertical position and order are in use by the algorithm. They're not showing anything directly in the dataset itself, but the algorithm is using that, in this case, to form these hierarchical containment relationships because it's cumulative. As you go up from leaves to their parent nodes, then that parent's poly expresses cumulatively that quantitative attribute in size, which is encompassed by all of its leaf nodes. So because we've got shared boundaries, then we can't use anything else to change the symbol or the shape or the orientation. We are free to color code, and that is typically done. So what these are really, really good for is finding extreme values. So you could also see like the distribution of attribute values. But what's very, very common is that to use tree maps for things like disk space. Right? Notice how it jumps out at you. There's that giant gray one on the upper right. There's a really big purple one, and then we see a whole bunch of much smaller things. So extreme values, in particular extreme high values, is what really, really jumps out with tree maps. We also can see some of that hierarchical structure. So the scalability, just like all these sort of grid-style things, at absolute maximum, 1 million nodes. So this is an approach where we're using enclosure. So we've now talked about two different approaches for showing links. We could use connection marks, or we could use containment marks. So a connection mark, right, that's a segment that is all the node link diagrams are using these connection marks. It's really good for understanding topological structure and tracing paths. We can use it for both networks and trees. Now, containment, using an enclosing polymark, we can only use that for trees because we need to have one parent for every child. So we couldn't use that for a general network. We can use that for trees, and it's really emphasizing an attribute value with the leaves. Well, what else could we do? Well, what if we didn't actually draw those links as marks? What if we just implicitly laid them out so that instead of using connection or containment, we just put the marks right next to each other for the nodes? We could do this radially. Here's an example of a diagram called sunburst, or we could do this rectilinearly. That's what's typically called an icicle plot. So With tree map, what's explicitly drawn as marks is basically the leaves, and then we have this implied structure of their parents. Uh, with sunburst, we're showing both the inner nodes and the leaves. Um, and with icicle plots, again, we also have a big area in which we're seeing those inner nodes, those subtrees. So this is another alternative. We could just implicitly show the links with spatial position and order rather than with a new mark. So it's interesting just to compare. Here's, a whole bunch of different ways to draw a tree. What do we see here? Well, what data are we even showing? Well, there's definitely this idea of the relationship between items, so that's the links. And a lot of these we're able to read off the depth in the tree pretty easily. In a lot of these, we might be able to see some ordering of siblings. So it's interesting to think about these design choices. I've talked really specifically today about the idea of a connection mark versus a containment mark versus something that implicitly shows the link with position. About, some of these layouts are rectilinear, Cartesian, some are radial, polar approaches. Um, Now, in a lot of these, spatial position is directly, maybe even the position itself might not mean something. In some cases, it actually does, but in some cases, the order is actually meaningful. So when are we directly able to read things off with position? When are we using order to actually mean something? And when does it not mean very much at all? Another thing to think about, which I haven't talked about yet, is, um, well, you know, what's redundant, what's arbitrary, and particularly from an information density point of view, we do want to avoid wasting space, right? We want to use as few pixels as possible, but also maybe we need a lot of room to show labels. So look at these drawings and think, what if I had to have not just a single letter inside each one of these nodes? What if I had a long word or even a full phrase or a sentence? How could I fit that? Notice how some of these layouts are much more easily to accommodate a lot of text inside the mark, inside that node mark, whereas others have much smaller node marks that would not be able to have long text labels. So that's something else we could think about. So let me just point out there is a huge amount of work in tree drawing. One nice resource is treeviz.net, and there are, at this when I took this picture, there were 277 different techniques for drawing trees. You can look, radial versus rectilinear. Do they use connection marks or containment marks? Are they just two-dimensional or three-dimensional? So a lot of exploring you could do if you're interested in tree drawing. And of course, there's been continuing work in drawing trees. So we've talked through some major approaches to drawing networks and trees. Node link diagrams and adjacency matrices work for both. Enclosure is specifically just for trees, and doing these implicit things is also just for trees.